When a bee's foraging on flowers, she's picking up nectar and pollen, or maybe only nectar or only pollen. Uh, what are the processes by which she decides whether she's going to collect, say, pollen or not? If you look at the loads collected by a large number of bees, you basically collect them at the entrance when they come back. You capture them, you squeeze their honey crops, you take their nectar loads and see what they collected. You take their pollen loads and you weigh it. And if you plot it, it looks like this over and over again. We've done thousands of them, and they always look very similar to this particular diagram. First of all, the maximum load of pollen that's collected is around 30 milligrams. And that represents bees that collect no nectar. So here's the nectar scale, here's the pollen scale. So these here collected only pollen and no nectar. These over here collected only nectar and no pollen. And they collected about 60 milligrams of nectar in their loads. But then you can see bees all along this axis here, this line, where they collected less nectar, but they didn't collect pollen. And here they collected less pollen, but no nectar. And then here you have a whole bunch in the middle who collected both pollen and nectar at different degrees. Well, I call this a foraging bias. And the foraging bias can lie anywhere within this domain. So does this represent just pure chance of what the bees collected or whatever? Or does this reflect some kind of distinct loading algorithms that bees have when they leave the nest to go out and collect? They have some sort of set algorithms by which they're going to be collecting loads that have so much pollen and so much nectar, or only be pollen or nectar forage. And this is a diagram, a model, a descriptive model for how, at least I think it works. You have loading algorithms. These are simply whatever kinds of neurological factors are going on that govern a bee's behavior when she leaves the nest to go out and collect pollen and nectar. And we know that when they leave the nest that they do have some sort of target that they're shooting for with respect to pollen or nectar. But what filters in? What are the components that determine these loading algorithms? And they come from different elements of their environment. This is their internal environment, and I'll talk about that, how that is affecting their loading algorithm, sort of this goal that they're having when they go to forage. The nest environment, they sample the environment of the nest, and it has inputs into determining what this loading algorithm will be. And then there's also the resource stimulus environment, and that's obvious when you start looking at the loads when there's a really high quality nectar out there. These algorithms that they use will shift more towards nectar foraging, and that can be demonstrated. The intake of pollen into the nest by pollen foragers, as can be seen here, coming in. The intake of pollen is determined, again, by the loading algorithms of the foraging population and the resource availability. If it isn't out there, it doesn't matter what your goal might have been when you left the nest, you're only going to be able to collect what's available. But this then feeds into the intake of the pollen into the nest. Then there are the nest stimuli themselves. The pollen comes in, you have the intake of pollen. Pollen comes in and it gets stored. It's stored in the nest. The stored pollen then is consumed by nurse bees who take the proteins that are contained in the pollen and they convert it into proteinaceous glandular secretions in the head that they then feed to the larvae. So if there's pollen coming in, it's going to get fed to larvae. If larvae are eating it, then the pollen gets consumed, and so there's more empty cells in the areas where the pollen is being stored. And these are two different stimuli that affect the nest stimulus environment. Stored pollen inhibits pollen foraging. You can take a nest, a colony, that is at an equilibrium with respect. It has the pollen's coming in, the larvae are consuming it, the nectar's coming in, we have the honey stores. And if you look at that, it will have a a pollen storage set point that if you disturb it, it will actually affect the pollen foragers at the entrance. So if you add a comb of pollen into a colony that's at this equilibrium, the set point, they've reached it, the foraging force will respond by having fewer pollen foragers. So if you ran around to the entrance and you looked at the entrance, you'd see, oh, there's fewer pollen foragers now. They have a surplus of pollen compared to what their set point was for pollen stores. That's based on how many larvae they have. So the pollen intake decreases when you have a large amount of stored pollen. But if you decrease the larvae, the number of larvae, they will also decrease their amount of pollen foraging. And I say also that with the stored pollen, the decrease in the pollen foragers will remain until they've consumed the surplus pollen, and then it will go back to where it was. If you take pollen away from them, they will actually increase their pollen foraging, more pollen foragers with bigger loads, until they bring it back up to where they had it. And then larvae works the same way, only larvae are a positive stimulus. They stimulate the pollen foraging activities of bees. So if you add larvae to a colony, they'll forage more. If you take larvae away, they will forage less. So these two inputs, stored pollen and larvae, these two stimuli then constitute the nest stimulus environment. A forager, when she returns, a pollen forager, will find the combs that contain brood and pollen. So the pollen is stored very close to the brood in a thin band around the brood on a comb. So if you take a comb out and you look at it, it'll look something like this. It'll have honey across the top and to the sides. Then there'll be a thin band of pollen, and then the brood will be towards the center and the bottom part of the comb. Well, the pollen foragers will go in and they'll walk along this boundary, and they're looking for cells where they can unload. And those cells are probably cells that have been consumed and fed to the brood at some point, so they're replenishing those. So they have an opportunity to come into contact with both the brood and the pollen stimulus, the plus and the minus stimuli for pollen foraging. Brood, it has two effects. It's both a releaser and a primer of foraging behavior, or pollen foraging behavior. The brood produce pheromones. These are chemicals that they produce in special glands that are secreted to the external of the brood, the larvae, and then the other workers will be exposed to that, and it will either release pollen foraging, meaning they'll go forage on pollen, or it will prime them to forage on pollen when they get older. Early nurse bees, before they forage, they're too young to be foragers. But when they're exposed to these primer pheromones, they will be more likely to collect pollen than if they weren't exposed to these primer pheromones. So it does two things. It releases the pollen foraging behavior immediately, and it also primes the younger bees to become pollen foragers when they are older. The other factor here are these internal factors. And they're also very important. We've shown over many years that the nest stimulus environment can explain about 5 to 8% of the loading algorithms. But these internal factors here can explain somewhere between 8 and 25%, depending on the different experiments that we do. So you have genotype. I mean, we can select bees using artificial selection. We can select bees that are more likely to collect pollen or less likely to collect pollen. So it shows that there's a genetic component to some of this variation in pollen and nectar foraging that you see. And the genotype affects ovary development. So bees are facultatively sterile. They still have reproductive organs. The organs still work in different ways with respect to furnishing hormones and whatnot, even if they aren't actively laying eggs. They will lay eggs in the absence of a queen, but they have small, reduced ovaries, and so they can't lay very many eggs. But their ovaries do still produce or regulate the production of vitellogenin, which is an egg yolk protein that also acts like a hormone and has broad effects on foraging behavior. And one of the effects it has is it tunes the sensory systems of bees. It makes them more sensitive to certain stimuli in the environment. So you have genotypes, affects ovary development, that affects the vitellogenin production, which can affect sensory response systems and tunes the system, which then in turn affects these loading algorithms. So here we have a bee that's being tested with different solutions of sucrose. The syringe that comes over to the bee is in this confined tube with her eyes are painted black so she can't see these things that approach her. When the syringe with the droplet is touched to her antenna, she reflexively extends her proboscis. She can't not do it. It's a reflex, like tapping your knee and having your leg jerk. So they can touch the antennae, the proboscis comes out, and we can measure her response threshold to sugar. And looking again at this idea of the response system here that's being determined by genotype, ovary, vitellogenin, sensory response, then that feeds into these loading algorithms. So we took some newly emerged bees. These are bees that just came out of the comb. They're brand new bees. And we paint marked them. Here's a batch of them that have been paint marked. They were then placed into a hive where they aged for 4 days. And when they were 4 days old, we went out and we collected the bees that had the paint marks on them. We took them into the lab and we put them in these tubes and we tested for their responsiveness to sugar. We did a concentration series that started with pure water and it went up through 30% sugar. So we would go down each bee, touch her antenna with water, and see if her proboscis came out or not. Then we went to 0.1%, 0.3, 1, 3, 10, and 30%, a logarithmic scale of concentrations, and determined the concentration at which the bee would first extend her proboscis. That was her response threshold to sugar. It's an indicator of the tuning of her sensory system. We then recorded what the response threshold was of that bee, and we put a little plastic number tag on her, and we put her back into the colony and waited for her to start foraging. So we could take any one of these bees, and we could look at her color, and for instance, red 28. Maybe she had a response threshold to sugar of 0.3%. And maybe white 11 was 30%. So we had all this registered. Then the bees would start foraging about 3 weeks later. And when they returned from their loads, all the bees that had the tags on them, we would collect, take them into the lab, and we would remove their nectar loads, check the concentration of the sugar they collected, and we would also remove their pollen loads and look at the weight of the pollen that they collected. This was the result that we got. So this over here is showing their sugar responses. The lower the number, the lower the concentration of sugar to which they responded, meaning they were more sensitive to sugar. Their sensory systems were tuned to be more responsive to the lower concentrations. And these up here are only responded to the very highest concentrations of sugar. So the bees that returned with water, they didn't collect pollen or nectar, they just collected water. They had the lowest response thresholds to sugar, meaning they responded to the lowest concentrations of the sugar solutions. And then that was followed by the pollen foragers, and then nectar foragers, those that collected both. And there was actually a large number of bees that collected nothing. And these were the bees that were the least responsive to the sugar concentrations in the test that we gave. In addition, if you look at the concentration of the nectar that the bees returned with to the nest, it correlated negatively with their response, their sucrose response. So not only was the tuning of their sensory system that we could detect using this sucrose response test, not only was it determining what they collected, but also with respect to nectar, the concentrations of the nectar in the flowers that they found to be acceptable. We don't believe that the sucrose response to sucrose is driving everything. The response to sucrose is a probe into the brains of the bees, is a probe into their sensory response system, where we can find one thing we can show has been tuned by the internal factors that I showed in the other figure that can be used as part of that, incorporated into that loading algorithm and used when they make decisions in the field about what to collect.